today's class we are going to discuss about Ampere Circuital law. Ampere Circuital law states that this is the basic law behind the concept of magnetostatics. Ampere Circuital law states that line integral of magnetic field intensity over a closed path is equal to the total current enclosed by the path. Okay, first we are going to prove the Ampere Circuital law. For that, what I am doing is I am just considering an infinite long straight conductor for which we have derived the value Bp is equal to mu I divided by 2 pi r. So now we are considering line integral B dot dl. So instead of B, I can replace that by mu I by the 2 pi r into dl. Take out the constant outside, mu I divided by 2 pi r into line integral. The limit is, upper limit is 2 pi r and lower limit is 0, and we are just going to integrate the above equation, the upper limit minus lower limit. So the answer is mu I divided by 2 pi r. When we substitute the upper limit, it is 2 pi r minus 0, then it is 2 pi r get cancelled, leaving out mu I. So we know that relation line integral B dot dl is equal to mu into I. So bringing the mu to the left hand side, line integral B by mu into dl is equal to I. So instead of B by mu, I can replace that by line integral H dot dl is equal to current enclosed. This proves the Ampere Circuital law. Now we are going to see the applications of Ampere Circuital law. The first application is we are going to find out the magnetic field intensity due to infinite long straight conductor, for which we are considering an infinite long straight conductor placed on the z-axis carrying a current I, and we have the Amperian path that is represented at the distance r, and let I be the current flowing through the conductor, and let the conductor placed on the z-axis. So now what we are going to do is we are just going to consider the cylindrical coordinates, that is r phi z. First we have to find out h. H is represented in terms of its vector form. H is equal to h phi into a phi, and similarly dl is equal to r into d phi into a phi. By Ampere Circuital law, we know that line integral h dot dl is equal to I. Therefore line integral h phi a phi dot, instead of dl, r d phi a phi is equal to I. A phi dot a phi, the value is 1, and therefore we get line integral h phi r d phi is equal to I. So taking the constant outside h phi r, the remaining thing is line integral 0 to 2 pi d phi, which is equal to I. So when we integrate d phi, we get phi, that is upper limit is 2 pi, lower limit is 0. So the answer becomes h phi r into 2 pi is equal to I, from which I need h phi. So taking the other terms to the right hand side, h phi is equal to I divided by 2 pi r. So now we need to find out the value of h. H is equal to h phi into a phi vector. So now we got h phi, it is I by 2 pi r. Just multiply that with a phi vector, we get the value of h. So that is the equation for h vector for an infinite long straight conductor. Next, what we are going to show is h vector due to a coaxial cable. So now you could say we are just considering a coaxial cable which consists of an outer conductor and inner conductor. The inner conductor carries a current I, and the outer conductor carries a current minus I, and the radius is A and B respectively. Now the cable is placed along the z-axis. The outer conductor carries a current minus I. So therefore we are just considering four regions. Region 1, r less than a. We know the area of the Amperian path, it is pi r square. The area of the inner conductor is pi a square. The current enclosed by the path is given by I dash is equal to pi r square divided by pi a square into I. Therefore I dash is equal to pi and pi get cancelled, leaving out I dash is equal to r square divided by a square into I. We know that by Ampere Circuital law, line integral h dot dl is equal to I. H dot dl is equal to I dash. We know that h is equal to h phi a phi vector, and dl is equal to r d phi a phi vector, and therefore just substituting those values, line it becomes line integral h phi d phi vector dot r d phi a phi vector, which is equal to I dash, h phi r integral 0 to 2 pi integration d phi is equal to r square divided by a square into I. So h phi r into, when you just substitute the limit, the upper limit is 2 pi. So h phi r 2 pi is equal to r square by a square into I. Therefore h phi is equal to I r square divided by 2 pi r a square. So r and r can be cancelled. So h phi is equal to I r divided by 2 pi a square. Now the cable is placed along this y axis. This is what we discussed. Therefore h vector is equal to I r divided by 2 pi a square. The second region is a less than r less than b. So here we are just considering the case of infinite long straight conductor. This we have already discussed. Value of h is given by h is equal to I divided by 2 pi r into a phi vector. So the answer is going to be the same for region 2. For region 3, condition is b less than r less than c, which means the b conductor is placed inside and c is the outer conductor and r is the Amperian path. Now the current of the outer conductor is minus I. The area of the Amperian path is given by pi of r square minus b square. The area of the outer conductor is given by pi of c square minus b square. Therefore the total current by the outer conductor is given by I dash is equal to, that is, the Amperian path is pi of r square minus b square and the outer conductor is pi of c square minus b square into minus I. Pi and pi get cancelled, leaving out I dash is equal to minus r square minus b square divided by c square minus b square into I. Therefore the total current is given by I dash, I enclosed is equal to I dash plus I. That is, for I dash it is minus r square minus b square divided by c square minus b square into I plus the total current I. So just both the terms current is common, so taking the current is outside, we get 1 minus r square minus b square divided by c square minus b square. This cross multiplying, we get c square minus b square minus r square plus b square divided by c square minus b square. So from which you can say I enclosed is equal to I into c square minus r square divided by c square minus b square. By Ampere Circuital law, line integral h dot dl is equal to current enclosed. So this we have already discussed. So if you just calculate the value, the final answer, it is found to be h vector is equal to I divided by 2 pi r into c square minus r square divided by c square minus b square into a phi vector. And the last region is r greater than c. So outside the conductor, we know the value of current is equal to 0. Therefore line integral h dot dl is equal to 0. And this diagram represents the variation of the each regions. Now it has been represented, and you could see for the first region the value of h increases, okay, as r increases h also increases, and in the region b also it is keep on a till a it is increasing, so that is h is directly proportional to r. In b region h is inversely proportional to r, and therefore h value starts reducing. In the third region h is inversely proportional to r, again h value is getting reduced, and in the last region it becomes 0. That has been plotted. This is about the h vector for various shapes for a coaxial cable. That's it. Thank you.